Okay, in this video we will talk about Kirchhoff's laws. But before this, I think I need to show you the potential graph of the whole circuit first. Okay, so now let's say that the battery is connected with two resistors, and then the connecting wires are a perfect conductor. That means that the wire itself has no resistance. So you know that the potential graph of the circuit is like this. When you choose a point and then you cut open the circuit, and then you label the potential with every point on the circuit, it will be like this. This region and this region and this region and this region are called equipotential lines because the potential here is same, the potential here is same, the potential here is same, and the potential here is same. But then inside a resistor, you know that the potential will drop. Okay? And then I want you to imagine this whole circuit is like a mountain. Now let's say that there is some water on the mountain top. The water will flow down automatically due to the gravity. So the water current is like the electric current. When you want to increase the resistance, that means that you put some rocks or stones or whatever in the river so that the current can be reduced. And then what makes the current flows? That is the potential difference. Okay, which is the height of this mountain. The higher the mountain, the faster the water flows. Okay, the higher the V, the higher the I. Okay, but then when the water flows down to here, who are the ones who carry the water back to the mountain top? It is the battery. Okay, the battery uses its own energy to carry the current back to the mountain top so that the current can flow again. Okay, so this is the analogy of V equal to IR, which is of the circuit. You have to remember that the current will flow from a place of higher potential to a place of lower potential. And then inside a circuit, where are the places where the electric potential is maximum, which is the positive terminal of the battery. Okay, the positive terminal of the battery is the highest place where the electric potential is highest. The negative terminal of the battery is the place where the electric potential is minimum. And then you notice that when the point A is here, the point A is here, that means that this is the level of the initial electric potential, and then this is also the level of the final electric potential. So you know that inside one loop, the sum of all the potential change is 0. That means that if you start at this level, you will also end up with this level in a complete circuit. Okay? And then normally in this type of circuit, we can only know the potential difference. So if you want to define the voltage here is 0, that means what? That means that you have to draw something like this. You have to say that this point is Earth, and therefore this point has 0 potential. That means that this point, 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 and this point has 0 potential. Okay? If you don't label this one, we can only know the potential difference. We cannot know the exact electric potential at every single point. And then you have to know that the current flows from the region of higher electric potential to the region of lower electric potential. That means that the current flows here. And then the direction of the current is opposite to the direction of the electrons. That is, the electrons will flow from here to here. Okay? Okay, so you know that the direction of the current is the opposite of the direction of motion of the electrons. Because electrons are negatively charged particles, and then you know that the negatively charged particles will tend to move to region of high electric potential from region of low electric potential, and then the current will flow from a region of high electric potential to a region of low electric potential. Okay, so now I want to introduce you to two Kirchhoff's laws. The first Kirchhoff's law states that the summation of the currents at a junction in a circuit is equal to 0. That means that inside one junction, the total current entering this junction is equal to the total current leaving this junction. Okay, and then you know that current is just dq dt. That means that current is the rate of change of charge. So this law is based on conservation of charge. Kirchhoff's second law states that the summation of all the potential change inside a closed loop of a circuit is equal to 0. Okay, that means that inside this closed loop, the summation of the potential change is 0. That means that E1 is equal to IR1, which is plus IR2. Okay, and then when E1 is equal to IR1 plus IR2, you multiply this with I again. You know that IE is the power supplied by the battery. I square R1 plus I square R2 is the rate of heat dissipated in all the resistors. So this is what? This is conservation of energy. So you know that Kirchhoff's second law is based on conservation of energy. And then if you don't like to use this sign, you can also use this sign. That means that the summation of the electromotive force is equal to the summation of the potential difference, where the electromotive force is the energy provided or supplied to the charge, and then the potential difference is the energy used by the charge. Okay, these are resistors connected in series. From the Kirchhoff's second law, you know that the summation of the potential change inside this closed loop is equal to 0. Okay, so from this, you know that the equivalent resistance are like this. Okay, when the resistors are connected in series. So these are resistors connected in parallel. Just now you use Kirchhoff's second law, but then now you use Kirchhoff's first law, which states that the current entering a junction is equal to the current leaving that junction. Okay, so by using this formula, you can also get the equivalent resistance for the resistors connected in parallel. Okay, let's do some questions. A battery with EMF E and negligible internal resistance is connected to two resistors R1 and R2 in series. Derive the expression for the potential difference across R1. Okay, so you know that E equal to I R1 plus I R2. And then the potential difference across R1 is denoted as V1. V1 equal to I R1. And then what is I? I is E over R1 plus R2. Okay, so you get this. When you are asked to derive something, normally you will present your answer in the variables given by the question. For example, in this question, they don't give you current, right? So you cannot say that V1 equal to I R1 because they didn't give you the expression for I. You have to find something to be the expression for I so that you give your answer in the variables that you are given by the questions. A battery with EMF E and negligible internal resistance is connected to two resistors in parallel. Derive the expression for the current through R1. Okay, so you know that the potential difference across here is equal to the potential difference across here, which is also equal to the potential difference across here. Okay, so V equal to E equal to I1 times R1. So you know that I1 equal to E over R1. So this is your answer. And then I need to tell you this because I want you to know the equations for the current divider. Okay, IR is equal to I1 R1. Okay, because the potential difference across the battery is equal to the potential difference across the first resistor. And then the equivalent resistance is like this. So now on, you are able to know the equation of the current divider. I1 equal to I times R2 over R1 plus R2. Okay, so you know that the higher the value of R2, the higher the value of I1. And then actually this one is the equation for the potential divider. That means that the potential difference across R1, which is V1, is equal to R1 over R1 plus R2 times the E. So you know that the higher the value of R1, the higher the value of the potential difference across this resistor. Okay, please find the potential difference across R1. First of all, you can find the current, and then you use V equal to IR to find the potential difference across R1. Or you can straight away use the equation for the voltage divider, which is like this. R1 over R1 plus R2 times E. Okay? Then you are able to get the same answer. Please find the total power dissipated. Okay? So, first of all, you find the equivalent resistance. And then you use P equal to V squared over R or I squared R or VI to find the total power dissipated. Okay, find the current through R1. You can use this formula, which is the potential difference across the battery is equal to the potential difference across R1. Then you are able to get the current. Or you can find the equivalent resistance first, and then you find the total current out of the battery. That means that this 16 is the current here. Okay, the 16 ampere is the current here. And then you use the equation for the current divider. That means that the current here, which is I1, is equal to R2 over R1 plus R2 times this whole current. Therefore, you know that I1 is equal to 12A. And then from the Kirchhoff's first law, you know that 16 ampere minus 12 ampere is equal to 4 ampere. Okay? So now you can find the total power dissipated. The total power dissipated can be found by using these three equations. Okay? But then, of course, you still find the equivalent resistance of the whole circuit. A wire of radius R, which is made of a material of resistivity ρ, has a resistance R. If one thing of its outer radius is oxidized, the oxidized portion has resistivity 5 times that of the original material. What is the resistance of the wire? Okay, you know that the resistivity of the oxidized portion is 5 times of the resistivity of the material itself. And then you find the resistance of the oxidized portion and also of the material itself. And then you know that the two portions are connected in parallel. That means that if you are the current, you can choose to move through the material itself or to move through the oxidized portion itself. Okay, so you know that the resistance, they are connected in parallel. Only when this is the oxidized portion and then this is the material itself, and then you are the current, then you have no choice but to move through both of them. And this time, you only say that the resistance are connected in series. Okay, but of course, this one is impossible. The positor is like this. Okay, because the outer portion is oxidized and then the inner portion is not oxidized. Okay, please find the reading of the ammeter. You know that these two resistors are connected in parallel. So that means that you can simplify this into this. And then you also know that these two resistors are connected in parallel, so that you can simplify this into this. These three resistors are connected in series, so you can sum them up into 5 ohm. And then this time you can find the current V equal to IR. And then this current is the current that flows through here. Okay? So for example, let's say that I want you to find the current in here and also in here and also in here and also in here. How do you find? You use the equations of the current divider. That is, okay, so now you know that the current that moves through this 3 ohm resistor is 1.6 ampere, which is this 1.6 ampere. And then you know that 2.4 minus 1.6 is equal to 0.8. So 0.8 ampere flows through here. Okay, so when it comes to here, you know that they are the same resistors. So half of the current will flow through here and then half of the current will flow through here. That is 1.2 ampere here and then also 1.2 ampere here. Okay? So if the position of the ammeter is changed to, let's say here, then you know that the reading of the ammeter is 0.8 ampere. Okay, but then now the ammeter is here. So you know that the reading of the material should be 2.4 ampere, okay, which is here and also here and also here. Okay. And then the current flow through here is 1.2, the current flow through here is 1.2, the current flow through here is 0.8, the current flow through here is 1.6. An electric circuit consists of 3 resistors and 2 cells with negligible internal resistance. Given that 0.38 ampere current flows through the 2 ohm resistor and a current of 0.12 ampere flows through the resistor with resistance R, please find the current I which flows through the 5 ohm resistor. Okay, by using the Kirchhoff first law, you know that the summation of these two currents is equal to I. Please find the EMF E. Okay, by using loop 1, which is here, and then you draw a direction here. That means that you assume the EMF is greater than 4.5. Therefore, you draw the direction to be here. Okay, E minus 4.5 equal to 0.38 times 2 plus 0.5 times 5. Okay, and then you determine the resistance R. By using the loop 2 and the Kirchhoff second law, you know that E is equal to 0.12 times R plus 0.5 times 5. Okay, therefore you can get R. Find the potential difference between point P and point Q. Okay, this is 1.5 volt and then this is 6 volt. They are of opposite polarities. Therefore, you follow this because this is a greater value. Okay, so you draw a direction from here to here. That means that the current will flow from the positive terminal of this battery to the negative terminal of this battery via the whole circuit. So by using Kirchhoff's second law, you know that summation of E is equal to summation of IR. 6 minus 1.5, because they are of opposite polarity. Okay, if they are the same polarity, then 6 plus 1.5. Okay, so it's equal to 9I plus 3I plus 3I. Okay, therefore you can find the current. So you know that the current will flow from a higher electric potential to a lower electric potential. Okay, so by using this path, Vp minus 0.3 times 3 minus 1.5, because it's coming from a region of higher potential to a lower electric potential, because it's coming from the positive plate to the negative plate. Okay, and then minus 0.3 times 3 is equal to VQ. Therefore, you get this. However, if you want to use this path, it's also okay. That means that Vp plus 0.3 times 9, because it's going against the current flow here, so you use positive sign. And then minus 6 because it's going from the positive plate to negative plate, so you know that the potential drops, okay, is equal to VQ. Okay, so that means that the blue one is from here to here, the red one is from here to here. Okay, find the reading of the voltmeter. That means that I want you to find the potential difference between point P and point Q. By using Kirchhoff's second law, you know that the summation of E is equal to summation of IR. 9 minus 1.5, because they are of opposite polarity, okay, is equal to 40I plus 20I. Then you know that I is like this. So Vp minus the current times 20 ohm plus 9 volt is equal to VQ. Okay, this is positive sign because it's coming from the negative terminal to the positive terminal of the battery, so you know that the electric potential increases. Or you can also use this path, that is Vp plus 1.5 because it is coming from the negative plate to the positive plate, okay, plus the current times 40 ohm is equal to VQ. Here you use plus because you are going against the current flow, okay? Here you use negative because you are going along the current flow. But then either way, you are still able to get the same answer. A battery of EMF 12 volt, internal resistance 2 ohm, and another battery of EMF 6 volt without internal resistance are connected in parallel with a resistor of resistance 2 ohm. Find current I prime. Okay, by using the Kirchhoff's second law in the loop A, you know that 12 minus 6 equal to I1 times 2. Therefore, I1 equal to 3 ampere. This is the current that flows through this battery. And then in the second loop, which is this loop, 6 equal to I2 times 2. So you know that I2 equal to 3 ampere. 3 ampere is the current that passes through this resistor. And then by using Kirchhoff's first law, I1 equal to I prime plus I2. 3 equal to I prime plus 3. So you know that I prime equal to 0. That means that no current flow through here. Write 3 equations by using Kirchhoff's law. Okay, first of all, you use Kirchhoff's first law. I1 plus I2 equal to I3 at this junction. Then you use Kirchhoff's second law for these two different loops. And then you are able to get 3 equations. And then now you have 3 variables. And then you also have 3 equations. Therefore, you can solve for I1, I2, and also I3. I3 equal to this, I1 equal to this, and I2 equal to this. You notice that I1 has a negative value. That means that in the circuit, the current is coming from here to here. Okay, but then in reality, the current is of the opposite direction. So find the potential difference across the resistor of 6 ohm. You can use V equal to I3 times 6, or you can use this path, or you can use this path to find the answer. Okay, for example, if you want to use this path from here to here, you are going from the negative terminal to positive terminal, so you use positive 12 minus 2 I2 because you are going along the direction of the current. Okay, then you can get 7.2. Or maybe you can also use this path. That means that from here to here, you are going from negative plate to positive plate, so it is positive 6. And then you are going along the direction of the current, so minus I1 plus 1 ohm. And then I1 is negative 1.2. Then you substitute here. You are also able to get the same answer. Two dry cells of EMF 12 volt and 9 volt respectively, and each of them has an internal resistance of 2 ohm and are connected in parallel. The cells are connected in series with a switch S and a bulb of resistance R. When S is open, find the current measured by the ammeter. When S is open, therefore you ignore this whole thing. Okay, you ignore this whole thing. And then by using Kirchhoff's second law in this loop, you know that 12 minus 9 equal to I times 2 plus I times 2. Therefore, you can get the current. Okay, so now when S is closed, the reading of the ammeter here is 0. That means that no current flow here. Okay, there's no current flowing here. Then by using the Kirchhoff's second law, you know that 12 minus 9 equal to I1 times 2 plus 0 times 2 here. Okay, because no current flows through here. And then you remember that I1 is the current that flows here in this loop only. Okay, I1 flows here. And then by using the Kirchhoff's second law in the upper loop, you know that 12 equal to I1 times 2 plus I1 times this resistance R. Okay, therefore you can get R. And then please calculate the power dissipated by the bulb. P equal to I1 squared times R. Okay, then you can get the power. A battery with an EMF of 15 volt is connected to resistors. If X is Earth, the potential difference at Y is, okay, when this is Earth, you know that the potential here is equal to 0. Okay, and then you know that these two resistors are connected in series. So 6 plus 12 equal to 18 ohm. And then this is connected in parallel with this. So once again, you can simplify the diagram. And then finally, you can find the current that flows through here and here and here. Okay, so the current flows through here is 0.92 ampere. And then you know that Vx minus 0.92 times 11 equal to Vy. Okay, because you know that the current will flow from a region of higher electric potential to a region of lower electric potential. Okay, so the answer for potential at point Y is negative 10 volt. Find the electric potential at point P with respect to point Q. That is Vp minus Vq. Alright, so by using Kirchhoff's second law, you are able to get the current. And then, okay, let's say if you want to use this path, Vp minus 6, because you are going from the positive plate to the negative plate, so you know that the potential drops. Okay, and then minus 5 times the current, because you are going along the direction of the current flow. Okay, and then plus 12, because you are going from the negative terminal of battery to positive terminal of battery, so you know that the potential rises is equal to Vq. Okay, so by using this path, we are able to get this answer. Or you can also use this path. That is Vp plus 3i, because you are going against the current, so you use positive, okay, plus 3i. And then plus 1.5, because you are going from the negative plate to the positive plate, okay, so you know that the potential rises. And then plus 8i, because you are going against the current flow, is equal to Vq. And then by this path, you can also get the same answer. Okay, the voltmeter has an infinite resistance. Find the reading of the voltmeter. If the voltmeter has an infinite resistance, that means that no current flows through the voltmeter. Okay? Therefore, actually you can simplify the whole diagram into this. Okay? Because there's no current flowing from point X to point Y, therefore this does not exist anymore. And therefore, you can simplify the whole diagram into this, and then finally you can find the current, which is 0.15 ampere, which is the current flowing out of the battery. And then by using the equations for the current divider, you know that the current that flows through here is 0.05 ampere, and then the current flows through here is 0.1 ampere. And then I want you to find the reading of the voltmeter. That is, I want to find the potential difference across here. So you know that Vx plus 0.05 times 30, you use positive sign because you are going against the current flow. And then minus 0.1 times 10 equal to Vy, okay? Or you can also use this path, which is Vx minus 0.05 times 10 plus 0.1 times 10 equal to Vy, okay? Remember, when you are going along with the current, then the potential drops. When you are going against the current flow, the potential rises, okay? So by using either path, you can get the same answer. But then you can solve this problem from the perspective of a potential divider. That is, the potential difference across here is 2 volt. And then this resistance is same as this resistance. So you know that here is 1 volt, this is also 1 volt. And then 3 over 3 plus 1 times 2 is equal to 1.5. Okay, so you know that the potential difference across here is 1.5 volt, and then the potential difference across here is 0.5 volt. And then by using some earth sign, you determine that the potential here is 0, so the potential here is 2. Okay, so the potential here is 0.5 volt, and then the potential here is 1 volt. Okay, 1 volt minus 0.5 volt is equal to 0.5 volt. So you are still able to get the same answer. Two resistors R1 and R2 and a thermistor are connected to a battery E of negligible internal resistance. The EMF of the battery is 6 volt. The resistance of R1 and R2 are 2000 and 5000 ohm respectively. Explain the changes in potential difference across R1 as the temperature of the thermistor increases. Actually, we have two types of thermistor, which is NTC and PTC type. For the NTC type, when the temperature increases, the resistance drops. But for the PTC types, when the temperature rises, resistance increases. However, these are not in your syllabus, so you recall what you have learned in chapter 14. That is, how the electrical conductivity of the conductor depends on the change in temperature, and also how the conductivity of the semiconductor depends on the change in temperature. If the temperature rises, the electric conductivity of conductor decreases. If temperature rises, the conductivity of semiconductor increases. So, actually, a thermistor is made out of semiconductor. So you know that when temperature rises, the conductivity of the semiconductor increases because there are more charge carriers, and then the resistivity decreases, and then you know that R equal to rho L over A. So when rho decreases, R also decreases. Okay, so you know that the resistance of the thermistor decreases when temperature increases. So you know that the equivalent resistance of both R2 and the thermistor, which is here, decreases because the resistance of the thermistor itself decreases. So the potential difference across R2 and the potential difference across thermistor decreases. Therefore, the potential difference across R1 increases, okay? Because E is equal to the potential difference across here plus the potential difference across here, okay? And the potential difference across R2 is the same as the potential difference across thermistor. So the key part of this problem is that you really have to know that a thermistor is made of semiconductor, and then you recall what you have learned in the last chapter. Okay? So determine the resistance of thermistor when the potential difference across R1 is 4 volt. This is 6 volt. This is 4 volt. So here is 2 volt. Okay? Or you can use the equations for the potential divider. That is 4 equal to R1 over R1 plus the equivalent resistance here, which is R2T times 6. Okay? And then you can solve for R2T. And then you know that the equivalent resistance of here is 1000 ohm. So 1 over 1000 is equal to 1 over 5000 plus 1 over resistance of the thermistor RT. Okay, therefore you can find the resistance of the thermistor. Remember that thermistor is thermoresistor. That is, the resistance depends on temperature. So when it comes to LDR, which is light dependent resistor, you know that the resistance depends on the intensity of the light. Normally, when it's in bright light, the resistance is very high. When it's in dark, the resistance is very low. Okay, so the LDR is connected in series to a resistor of 2 kilo ohm and a voltage supply of 9 volt. Please determine the voltage VAX, which is the potential difference across the LDR in bright light. Okay, you know that in bright light, the resistance of this one is 1 kilo ohm. So you use the potential divider formula. 1 over 1 plus 2 times 9 equal to 3. Okay, calculate the resistance of R, which is this one. If VAX is 2.75 volt in bright light. Okay, so once again you use the equation for the potential divider. So now you know that the resistance of this resistor is 2273 ohm. If another similar LDR is placed in parallel to the first LDR, please calculate the VAX in bright light. You know that the resistance of one LDR is 1 kilo ohm. And then when there are two similar LDRs connected in parallel, the equivalent resistance is now 500 ohm. Okay, and then once again you use the equation for the potential divider to find the potential difference. Okay, in next video we will be talking about voltmeter, ammeter, shunt, and also multiplier.